The topic of the day is identities, and basically what an identity is it's just a true equation, and there are several identities that we already know about, and they're listed right in front of you. You've got the cosecant's the reciprocal of sine, secant's the reciprocal of cosine, and the cotangent's the reciprocal of tangent. So we know all that. We've already identified those. But it's also true and sometimes needed to state that sine is a reciprocal of cosecant, cosecant's a reciprocal of secant, tangent's a reciprocal of cotangent, and we know that tangent is basically sine over cosine. We can also say that cotangent is equal to cosine over sine. Right? Those are the ones we know already. Now, we also know the following. We know that if we have a unit circle, or any circle for that matter, with the center at 0, 0, we know that the equation of that circle is x squared plus y squared equals r squared. Given that it's a unit circle, we can say that the radius is 1, so we can say that x squared plus y squared is equal to 1 squared, and we get that from the right triangle with hypotenuse of 1 and a horizontal and a vertical length. So if we apply that to sines and cosines and assume we're on the unit circle, we can say then that cosine is going to be our x, sine is going to be our y, and therefore we have this new identity of sine squared sine squared plus cosine squared is equal to 1. This identity here is probably one of the most prevalent identities you're going to be using for the next, couple of weeks. Now, off this identity come several more. All right. In fact, if we were to take and divide each term by a number, because algebra lets us do that, in fact, we're going to divide each term by sine squared. Notice sine squared over sine squared, cosine squared over sine squared, and 1 over sine squared. We get a new identity of 1 plus cotangent squared is equal to cosecant squared. And this is used quite often as well. If we were to take and divide each term in sine squared plus cosine squared equals 1 by cosine squared, we get once again another identity, or tangent squared plus 1 is equal to secant squared. All three of these identities are what's known as a set of Pythagorean identities. So here they all are. These you need to get down because these are, like I said, the most often used identities when we start doing verifications and proofs. Now, again, from these can hide themselves within different types of equations. Each of these simple Pythagorean identities could break down into 3 other Pythagorean identities by just taking and doing a subtraction. So if on this first term I take and subtract off cosine squared, then I have sine squared equals 1 minus cosine squared. There's a true relationship. Likewise, if I took sine squared and subtracted it from the other side, I get 1 minus sine squared equals to cosine squared. It's just you need to start recognizing the base form of the 3 identities known as the Pythagorean identities here. Alright, so let's move on. So we're going to start with the algebraic verification rather than a trigonometric verification, in that we're going to show that the left side of this equation is equal to the right side. Basically, it's a simplification problem. If I were to pull 2x out of the first term, I end up with x squared plus 3x plus 2 over, pull out a 5x on the second term, and I get x plus 1. Top term continues to factor, and I get 2x times x plus 2 and x plus 1 over 5x times x plus 1, and do the proper reductions. The x's go away, and I'm left with 2 times x plus 2 over 5. So this was just a general example of how you get one side to equal another. Now we're going to start doing this with trigonometric formulas. So I want to show that the cosecant times 1 minus the cosine squared is equal to the sine squared. Well, if I look at, or was equal to sine, I'm sorry. So if I look at this term right here, and I say, that looks a lot like Pythagorean identity. In fact, it is. 1 minus cosine squared is equal to sine squared. And you can look back at your notes and see that that's a true situation. Cosecant is equal to 1 over sine. The goal is to get as many sines in the problem as you can, so you end up with sine by itself. So this is now a set of fractions multiplied by each other, and notice the signs reduce. So I end up with sine of x equals sine of x. Now, the truth about verifications is you only can work one side. And this is the case because if you remember back to geometry proofs, you could really only use the given to get down to the prove. You couldn't use the prove necessarily as a step. Same idea. This is kind of like the prove over on the right side here, and this is like the given, and you have to work from the given to the prove. So again, here's another verification we're trying to get in the end to a sine, or for that matter, you could try to work over to here, but I usually try to get to the simplest looking term. Sine is that in this case. So I know cosecant, if I want to get as many sines as I can in the problem, cosecant is 1 over sine of x. Cosine, I can't really do anything with that. Cotangent, I can call cotangent cosine of x over sine of x. So now, cosine times cosine is cosine squared, and I have common denominators of sine, so that's 1 minus cosine squared of x over sine. From our last problem, we know that 1 minus cosine squared is a Pythagorean identity of sine squared. And then I have sine squared over sine, which is just sine. And that's what I wanted to get to. Here's another problem, and you'll notice all these are equaling sine right now. It just turned out that way. That's not always the case. I have a couple of options here. I can take and try to change all these now into forms of sine, all right? Or I can just do a multiplication if I wanted to. Doesn't really make a difference to me. I'd rather leave fractions out of the problem until I have to put them in. So I'm going to take and FOIL this. Notice 1 minus cosine is not a Pythagorean identity. 1 minus cosine squared is a Pythagorean identity. So once again, let's FOIL this. I have cosecant of x minus cosecant of x cosine of x plus cotangent of x minus cotan of x cosine of x. And all of this is supposed to equal sine of x. So let's go through and start changing things now. I've got 1 over sine here minus cosine over sine because cosecant is 1 over sine. Cotangent is simply cosine over sine. Once again, cosine over sine, and that's times cosine. So notice these two terms go. I'm left with 1 over sine minus cosine squared, starting to be a pattern, over sine. So I have 1 minus cosine squared over sine. We know 1 minus cosine squared is sine squared. If that one's not beat into your head by now, I don't know when it will be. And that's equal to sine, which is what we were trying to get to. Alright, so here's a couple more. We're trying to get everything to cotangent squared. This is actually the easiest form for me. I I could change this to cosine squared over sine squared, but I'm just going to go with the cotangent squared. I know it equals cosine squared over sine squared, so if I ever get that, I'm good to go. 1 plus cotangent squared, that looks a lot like a Pythagorean identity, and it is. It's actually cosecant squared. And 1 plus tan squared is also a Pythagorean identity. That's secant squared. And I don't really recognize this as cotangent squared. It could very much well be, but I like getting things in sines and cosines so I can make them look like tangents or cotangents. Cosecant squared is 1 over sine squared, and secant squared is 1 over cosine squared. Now I can multiply by the reciprocal of this denominator and get cosine squared over sine squared, which is cotangent squared, which is exactly what I wanted. Here's another one. We're trying to get 2 secant of x, which is really the same as 2 over cosine. So if I can get that, I'm happy. I notice I have a cosine in this denominator, so at least there's a start. But I'm asked to add these two fractions together, and I can't add them together unless I have a common denominator. So basically what I'm going to do is I'm going to say, all right, well, this term needs a cosine, so that's cosine over cosine. And that is tacked on to the first fraction. And then the second term needs a 1 plus sine. So this gives me a cosine squared. This term is going to give me, I'm going to FOIL this out, 1 plus 2 sine of x plus sine squared of x over, this is my common denominator now, cosine of x times 1 plus sine of x. I'm going to combine some like terms, which I don't have any, but I notice within this I've got sine squared plus cosine squared. That's a Pythagorean identity of 1. So that's 1 plus 1 plus 2 sine of x over cosine of x times 1 plus sine of x. Combine like terms. I have 2 plus 2 sine of x over cosine of x times 1 plus sine of x. Notice the numerator is going to factor. Pull out a 2, get 1 plus sine of x over cosine times 1 plus sine of x. Reduce. Get 2 over cosine of x. Now what do you know? That's the same as 2 times 1 over cosine of x, or 2 secant of x. And that's what I was looking for. Moving forward, we're going to try to get cotangent minus tangent over sine times cosine equal to this term. This might be a little bit more difficult. Cosecant squared minus secant squared. Looks like a Pythagorean identity, but it's not. I think I'll start by, well, I could go to all sines and cosines. That's always a possibility, but then I get a complex fraction. And I don't know that, well, I don't know that I have any choice. Let's go ahead and do that. What the heck? Cotangent is cosine of x over sine of x minus sine of x over cosine of x. And this is all going to be over sine of x, cosine of x. You've got a couple of options on this. You could choose to do the numerator and simplify that and then multiply by the reciprocal of the denominator. Remember, this is over 1 down here. Or I could multiply by the common denominator of both the numerator and denominator and go from there. I think what I'll do is multiply by sine cosine to the numerator and denominator, because that's the common denominator of both the numerator and denominator. You're going to have to distribute that and then multiply that through. So you'll notice I get cosine squared minus sine squared, which is not a Pythagorean identity, over sine squared cosine squared. Now, this is a subtraction I'm not allowed to reduce. However, what I am allowed to do, and this is one of the tricks in identities, sometimes while the simplified fraction looks pretty, it might be better to break it up, especially when your verification part, or what you're trying to get to, is a separated fraction. So I'm going to break this up into two fractions. It's almost like saying, well, if I know that 9/13 is equal to 2/13 plus 7/13, which may be true, it could also be represented as 2 plus 7 over 13. So I'm breaking it up into its parts. I'm going to do that here. Cosine squared of x over sine squared cosine squared minus sine squared over sine squared cosine squared. So now you'll notice these are separate fractions, and I can go ahead and reduce because there's no subtraction to reduce across. This ends up as 1 over sine squared, and this ends up as 1 over cosine squared. What do you know? 1 over sine squared is cosecant squared. 1 over cosine squared is secant squared, which is exactly what I was trying to get to. Let's keep going. This is going to be a long one today, so just hold on for the ride. We're going to need a common denominator once again in order to add these. So this term needs a secant minus 1 times secant plus 1 because I need the common denominator. So this again, secant x plus 1 over secant x plus 1. It's going to get multiplied by secant x minus 1 over tan x added to tan over tan times tan x over secant x plus 1. Multiplying through, I get secant squared x minus 1. That's the first term. The second term is going to be plus tan squared x all over tan of x and secant x plus 1. I know that 1 plus tan squared is secant squared. That's not going to be this because this is negative 1, but I also know that if 1 plus tan squared is secant squared, then secant squared minus 1 is tan squared. So if you'll notice, this term right here is a Pythagorean identity. So what I've got is I've got tan squared plus tan squared over tan times secant x plus 1. This gets me 2 tan squared over tan times secant x plus 1. Tans are going to reduce out, so we'll go ahead and get that done. That gives me 2 tan over secant x plus 1. Keep in mind what we're trying to get to. We're trying to get to 2 sine over 1 plus cosine. So we need to get all this in sines and cosines eventually. Let's do this now. So we'll go 2 sine over cosine, because that's my tangent. We'll go 1 over cosine plus 1. Multiply by cosine over cosine to get rid of the complex fractions. I end up with 2 sine over 1 plus cosine, and that's exactly what I want. So you'll notice in this problem that each of the terms are unable to be simplified. Sine doesn't simplify anything, cosine doesn't simplify into anything, likewise over here. So in that case, you're going to need a trick, and this tends to happen. When you no longer have any simplifications you can do, you want to look at the terms and say, well, what if I were to take and multiply it by some form of 1, which you can always do. For instance, if I needed to make a tangent in my problem, I could multiply the top and bottom of this side by 1 over cosine and 1 over cosine. And that would help me get a tangent. I've multiplied by 1, so I haven't changed the value. Algebra always holds true. But sometimes it's easier to take a look and say, wait, what if I multiply by a conjugate? So the conjugate I'm talking about in this case is 1 minus cosine, because that's a conjugate of 1 plus cosine. And oddly enough, 1 minus cosine is up here. I can't just multiply the bottom by that. I have to multiply by the top, because now I'm multiplying by 1. And you can always multiply 1 to anything and not change its value. But then again, I'll change its look. So here's what I have. I have 1 minus cosine of x times the sine of x. And I'm going to leave that like this rather than multiplying out. And I'll show you why in a second. The bottom is a difference of squares. It's 1 minus cosine squared of x. I know 1 minus cosine squared of x because we've seen that identity a couple of times today. We got 1 minus cosine of x times sine of x. 1 minus cosine squared is sine squared. Notice I have a sine over sine squared, which goes to 1 plus cosine of x over sine of x because of that reduction. And, whoops, I changed the sign right here, unfortunately. So I end up with 1 minus cosine of x over sine of x. It was a long one today. Hopefully you got something out of it. You're going to need to know those Pythagorean identities pretty well. And we'll once again go over this a little bit more tomorrow.